So here's the weird thing, right? It can be the case that the directional derivatives exist for a function like this in every single possible direction for the function. They can all exist. And yet, if you take the function and instead, so what's the directional derivative operationally? It's ddt of what? Ddt of f of p plus tu hat. And we evaluate at t equal to 0, right? That is the directional derivative in the u hat direction of f at p. So if you look at it, what we're doing is we're feeding f of x, we're feeding f a line, right? So we saw some really pathological things with path limits, right? In the study of multivariate functions and continuity, we saw that there are functions which, if you approach along a line in every different direction, they all go to 0 and match up. But then somehow, if you look at approaching parabolically, your limits end up separating and the limit doesn't actually exist. Something similar can happen here. It turns out there are functions where if you, instead of feeding this a line, if you feed it like a parabola that goes through the thing and study the rate of change of the function along a parabola, that it doesn't exist. So what I'm trying to say is it's possible for all the directional derivatives to exist, and yet there not to be a good sense in which the graph looks like this. The graph might actually have some kind of tear in it. Might look something like this. There might be like a tear in the graph, a discontinuity even. You can have a discontinuous graph, yet somehow all of the directional derivatives still exist. This kind of behavior is possible. However, it is not possible if we, this is going to be a little bit of an adventure. It is not possible. Hey, what? Come on, I said. Nope, I said. We'll eventually find my way here. By the way, guys, there are, well, I showed you some of these yesterday, but I hope if you go back and look at these now, they make more sense, right? You'll forgive my inability to navigate. Come on. So here's one. This is what we started with. That's x squared plus y squared. There's the gradient field. The contours are also plotted there. The shading of the contours tells you the values increasing from blue to red. Blue is smaller, red is bigger.
You can scroll with the touchpad. That's what actually the touchpad defined for.
Oh, this is touchpads for scrolling. So you notice here in the middle we have a claim that we proved today, right? I showed you the argument that the gradient vector field is perpendicular to the level curve. In the notes, this comes later because I refuse to talk about the chain rule until my chain rule section. But I've thought about these things more deeply, and so sometimes I'm a slave to organization in my note writing, right? That's just my nature. I have grouped together all of the chain rules in the chain rule section, right? But it's kind of more organic to talk about it earlier, which is why I've done it with you today. Right, rather than just delay it. I actually did that proof today. I've erased it. Oh. Anyway. So here's that physics example I was actually talking about, by the way. So this voltage function, this is 1 over the radius. That's actually the voltage for a point charge at the origin in 2 dimensions. And the gradient, minus the gradient of that, in physics we learned that's the electric field. Minus the gradient of the voltage function is the electric field. That's a very important physical application. This perpendicularity we've discovered today is exactly the perpendicularity you've talked about in physics if you've had it, that the equipotential lines, which are the contour lines of voltage, equal potential means equal voltage, means constant voltage along an equipotential line. Well, those are perpendicular to its gradient, and you go minus that because the electric field points in the direction in which charges flow, which happens to be not do charges flow to regions of less or more potential energy? Physics is lazy, right? So we go to systems with less potential energy, right? We roll down hills, not up hills. So that's why the minus is necessary, because the gradient points in the level up direction for the voltage, but physics says you level down, because nature's lazy. Anyway, the mathematics here, gradient of the vector field, reveals minus 1 over r squared r hat, which is, of course, the Coulomb field. The 1 over r squared field. All right, I'm digressing. That was not what I want to talk about. I mean, I don't mind talking about it, but here's another nice example with some contours and some levels, but I was trying to get something here today before I got distracted by my, oh man, 2 minutes, curses. This is a lot like one of your homework problems. This one right here. Here's another, so this I cannot do by hand, but here on the one side you have the contour plot, right? And then over here you have the graph where the shading of the graph illustrates the level, and that shading is actually in concert with that, which is kind of neat. Oh, I will eventually learn how to scroll on this thing. So there's a hyperbola, and the graph corresponding to the hyperbolas is what's called a saddle shape. This is a saddle shape graph, all right? Eventually, we'd like to learn how to use calculus to distinguish between saddle-shaped local extremas versus ones that are genuine min-maxes. Here's a funkier one. All right. Here's an example of why you shouldn't trust computers. Right? I mean, part of what one of our main goals and one of our sort of unstated goals, oops, about to state it, is that we want you to learn calculus well enough so that when a machine does something that's crazy, you can recognize it. And you know, wait a minute, my mathematical software is not doing what it's supposed to, right? This is not actually in the math. This is just an artifact of poor computation, right? It's a computer artifact. And here's, come on. There's that one. So we've already more or less differentiated in R3. The rules are pretty much the same. My better students complain that I've made this into 2 sections. This example 4.36 is kind of fun. Here's Nathaniel's daily quiz question done in Rn. Guess what? It's still xj over r, or u. I've defined u to be the square root of the sums of the squares of all n. Anyway, get to here. So continuously differentiable, what's that mean? Well, we'll talk about that next time. So, thanks, guys.